number 23. Not sure how to do the second version.
Chapter 7, number 73.
Yeah.
Let's take a look. This one here? Substitute natural gas, SNG, is gaseous mixture containing methane that can be used as a fuel. One reaction with production of SNG is when you take carbon monoxide and hydrogen in a redox reaction, you can reduce carbon monoxide. Hydrogen is a pretty good reducing agent to form methane, plus CO2 plus water. This is delta H reaction. So what are the ways we can get delta H? We can do calorimetry. And so if we do calorimetry, we get Q. And we'd have to do constant pressure calorimetry. But this might be hard to do at constant pressure. So we might end up doing constant volume calorimetry. If we do constant volume calorimetry, then we can get delta U. This is bomb calorimetry. This delta U is equal to QV. When there's no work that can be done, QV. Oops. Into this. And then if we have an amount, like how many grams were burned, then we can get it over the amount, and then we can get kilojoules per mole. Then we can figure out how much work is done. We can figure out how much work is done by looking at how many moles of gas we have here. 12 moles of gas going to 4 moles of gas. So we're losing 8 moles of gas. We're losing 8 moles of gas, so the system's going to shrink. The system shrinks. Surroundings does work. So we'll have to determine, if we do bomb, and then we want to do figure out what delta H is. We do delta H is equal to what? Delta U minus the work. And so we get delta U from the bomb, and then we calculate how much work is done by looking at how many moles of gas are consumed in this 8 moles of gas are consumed. We can do that. But that requires doing bomb calorimetry and then a subsequent calculation. And then we can get delta H from this. But there are other ways of getting delta H. What are the other ways of getting delta H? Well, the example here is by using a law. What's a law? Hess's law. There are 2 variations of Hess's law. One is just with random equations. This is Hess's law with a bunch of random equations. And then variation 2 of Hess's law is Hess's law using only one type of equation. And the one type of equation that we use is called a formation. So if we use a formation reaction, then we don't have to do all this addition and subtraction because everything else cancels out. It's got to cancel out in formation reactions. But anyway, what we got to do here is we do this. We need 4 carbon monoxide. This one has carbon monoxide, so we can use this one. Do any of the other reactions have carbon monoxide? This one has carbon monoxide as well. Do you see that? And so which one should we use? I don't know which one we should use, actually. So let's skip carbon monoxide because we have a choice. Let's go to one where we don't have a choice. And so the next species here is hydrogen. So I need 8 hydrogens. Which one of these has hydrogen? Well, 2 of these have hydrogen. So again, I have a choice. So let's skip that for now. How about methane? Which one of these has methane? The bottom 2. So I have a choice there. Then I go to CO2. if we go to CO2, these two have CO2, and then I go to water, and these two have water. So I have some choices there. I don't know, which way is the easiest, because I have no idea. And it would be nice if I didn't have a choice, then that fixes it for me. So since I don't know, what I'm going to do is just pick one. Which one do you think is going to be easier for carbon monoxide? Probably this second one, because I don't have to flip it around. Do you see that? And so I'm going to, what should I do? Double the, or quadruple the second one. You see that would yield, is the question how to do this? Or was there something else? No, we use the first version of this. In order to use the second version, we need the delta H's of formation. The delta H's of formation are in the appendix D, so we could use the second version easily. But they don't want us to use the second version. They want us to use the first version. And so using the first version, we have to add up all these equations to make that equation. So the first thing we do is get 4 carbon monoxides. So I'll do 4 carbon monoxides plus 4 times 1/2 is going to be 2 O2. This is going to yield 4 CO2. And then it's going to be 4 times minus 283. Right? Which comes as much. All right, so we have our 4 carbon monoxides. That gives us 4 CO2s, but we don't want 4 CO2s. How many CO2s do we want? We don't want 4 CO2s. We want 1 CO2. Do you see that? There. We only want 1 CO2, so we got to get rid of 3 CO2s. There's only one way to get rid of 3 CO2s. I cannot use this equation again. If I use this equation, then I'm going in circles, and I don't want to go in circles. So how can I get rid of 3 of the CO2s and leave me with just 1 CO2 here? There's only one way to do it. What other equation has CO2? Do you see it? It's got to be this one. This is the only way I can get rid of the CO2, is I have to flip this one backwards and then multiply it by, flip that one backwards and then multiply it by 3. So I'm going to get 3 CO2s here. If I get 3 CO2s here, then these 3 CO2s cancel and leave me with 1 CO2 there. And so that's my strategy for this. And so this is going to be 3 CO2s plus 6 H2O yields 3 CH4 plus 6 O2s. And so what I did was I made it backwards, which is going to change the sign to positive 890.3. And I multiplied it by 3, so it's 3 times positive 890.3. All right, the O2s, these 2 O2s are going to cancel 2 of those and leave me with 4 there. So am I getting any closer? Let's see what I've got here. So I don't want to mess with my CO2s and I don't want to mess with my carbon monoxide. But I need 8 H2s there. And I had 2 choices for the H2. I could use this one here, or I could use this one here. And then I need 3 CH4s. Well, I got 3 CH4s here already. So that's good. And so I don't want to mess with the CH4 if I don't have to. So I have 2 choices for H2. I'm not going to use the second one because that's going to mess with the CH4. I'm going to use the first one, which won't mess with the CH4. And so I'm going to get my 8 H2s that way. So I'm going to go 8 H2s plus 8 times 1/2 is 4 O2s is going to yield 8 H2Os. And since I multiplied this one by 8, this is going to be 8 times 2 minus 285.8. And that gives me this. This is what I want. I have my 8 H2s, 4 carbon monoxides plus 8 H2s. If I look at my O2s, take a look at what happened to my O2s. Do you see the 4 O2s here? The 4 O2s here cancel the 4 O2s there. And then let's take a look at the water. I want the 3 CH4s there. The waters, I have 6 waters here that's going to cancel out 6 here and leave me with 2 waters. And so do you see what happened here? Now I have 4 carbon monoxides plus 8 H2s yields 3 CH4s plus 2 waters plus 1 CO2. And it matches there. And so the overall equation is going to be 4 carbon monoxides plus 8 H2s yields CO2 plus 3 CH4 plus 2 waters. And then what we do is we add these up. This plus this gives us delta H for the net, or the overall reaction. So this is the Hess's Law version 1. Hess's Law version 2 would have been a lot easier. You know how we would have done Hess's Law version 2 is we just take the delta H as a formation of the products minus the delta H of formation of the reactants that we find in Appendix D. And so it's easier. Hess's Law version 2. What's that?
We can't do number 2 version for this one?
We can. We could do number 2. We could do number 2. But that's not what they said. They said use appropriate data from the following list. They didn't say to go to Appendix D. If we went to Appendix D, then we could have done this quickly. Or the data that they give you. Here they didn't give us the Appendix D data or tell us to go to Appendix D, so we had to use that data. We didn't end up using all the equations. We only ended up using 3, but that's only one path. Remember, I had a choice. Take path A or take path B. And not only did I have a choice of path A and path B, I had a choice for every single compound in there. So how many different variations could I have done? So if I chose path A instead of B, I would have ended up using a different set of equations. Does that make sense? And so there are a number of ways to solve this correctly. No. We can't use version 2 with this one. We could because all of them are the same, but in general, these are not heats of formation. These are heats of combustion. Version 2 requires heats of, but as long as all the reactions are the same type, if all these are combustion reactions, then it would have worked. This would have been version 3. Version 3 is just you doing the same thing as version 2, except with only combustion reactions. Yeah, but if you throw in a non-combustion reaction, then it's going to fail. All the reactions have to be exactly the same type, otherwise things don't cancel. In version 2, we don't cancel anything. Here we have to cancel everything because the reactions are random, they're different. When I look at the data that was given here, this is a formation reaction. Is this a formation reaction? No, because we're forming 1 mole of CO2, that's correct, but we're forming it from carbon monoxide, which is not an element. Oxygen is an element. Is this a formation reaction here? Yes. Is this a formation reaction here? Yes. Is this a formation reaction here? No, so it's a random mix of reaction types. We can't use the simplified version of it for this. If we only have one type of reaction, all combustion or all formation, then we could, because everything else is going to cancel. Okay, other questions? So let's take a look at some first law we have. Delta U is equal to Q plus W. It's equal to QV because the constant volume work is going to be 0. But in general, it doesn't have to be constant volume. It could be constant pressure. Let's look at the delta U. So let's look at 55. What is the change in internal energy of a system if the system absorbs 58 joules of heat? So the system absorbs 58 joules of heat. Is that positive or negative? Positive. And does 58 joules of work? If the system does 58 joules of work, is that positive or negative? Negative. And so we're going to have a plus 58 plus a minus 58, which is going to give us 0. So A, the change in internal energy, delta U 0. B, absorbs 125 joules. Absorbs 125 joules, that's plus 125 joules of heat. And does 687 joules of work. It's going to be plus a minus 687. And so the delta U is going to be negative. The internal energy is going to go down. C, evolves 280 calories. Is that positive or negative? Evolves. If it absorbs, it's positive. If it releases or evolves it, then it's negative. It's going to lose it. So evolve 280 calories is minus 280 calories. And has 1.25 kilojoules of work done on it. So if the system does work, it loses energy. That's why work is negative. We lose energy. But if the surroundings does work, then the system gains energy, and that energy is positive. And so this is plus 1.25. So this is minus 280 calories plus 1.25 kilojoules. So we got to get them in the same units. Once they're in the same units, then we can add them or combine them together. Let's take a look. There are two important processes that people talk about in thermodynamics. And that's expansion and contraction of gas. When the system expands, then work is done. Work is done because the system has to blow up the balloon. And so work is done by the system. Okay. When a system contracts, then the surroundings doesn't work, and we say that work is done on the system by the surroundings. And for expansion and contraction processes, there are two modes that we typically deal with it. If something expands and contracts, then it's already constant pressure. So both of these are constant pressure. But we can do this isothermal. Isothermal is when the system's in thermal contact with the surroundings. And so the system and the surroundings are essentially touching each other and can exchange heat back and forth. In other words, they're going to be at thermal equilibrium. They're going to be at the same thermal temperature. In adiabatic, the system and surroundings are isolated. And so there's no exchange. It would be like a thermos if the system were inside an insulated thermos. And it can't exchange heat. So let's look at 57 next. The internal energy of a fixed quantity of an ideal gas depends only on its temperature. Internal energy is the total energy. And the total energy of an ideal gas is going to be the sum of its potential energy plus its kinetic energy. But the weird thing about an ideal gas is, what is the ideal gas? For example, is the ideal gas helium or hydrogen? Or both helium and hydrogen? Or neither of them? And so an ideal gas, when we look at the ideal gas law, it never asks you whether you're dealing with helium or hydrogen. It doesn't matter, because an ideal gas law is just a little point in space. And so this point represents a helium atom, or this point represents a hydrogen molecule. And these points don't interact or react with one another. And so in an ideal gas, the potential energy is zero, because there are no electrons in it. There's no bonds. There's nothing. There's no interaction. And so in an ideal gas, the internal energy only depends on the kinetic energy. And the kinetic energy is a measure or the temperature is a measure of the average kinetic energy. And so it's going to be dictated by the temperature here. So if I have an ideal gas like this, and it expands like this, then the system expanding requires work. And therefore, work is done by the system. The system's blowing up the balloon. And therefore, the system's going to lose energy. And so we lose energy here, because some of that energy has to be used to expand the system volume. But if we lose energy here, it can only be in the form of kinetic energy. So if we have lower kinetic energy, how does that manifest itself? And what happens is, this is just going to be at a temperature that's got to be colder. And so let's say we started off at room temperature or warmer temperature, and then the gas expands, and the temperature's got to go down. Does that make sense? So in other words, the system does work and loses energy. The only energy an ideal gas can lose is kinetic energy. And so if it loses kinetic energy, the temperature is going to get colder. This actually has a name. This is called Joule-Thomson cooling when the gas expands.
Is it the same Joule?
Yeah, it's the same Joule as the energy Joule. The Joule-Thomson effect. In thermodynamics, the Joule-Thomson effect, also known as the Joule-Kelvin effect or the Joule-Kelvin-Joule effect, describes the temperature change of a real gas or liquid, as differentiated from an ideal gas when it's forced through a valve. Well, ideal gas, real gas, it's going to be comparable. In other words, it's going to be cooling. There's going to be cooling. Whatever. And so we're going to get this cooling effect. And so let's see what we can do. But this is like if you have the keyboard cleaner or aerosol can and you're spraying the gas out of the can gets cold. But does the can stay cold forever? No, what happens is the can is going to warm back up to room temperature because we live in this huge what should we call it? Heat sink? In other words, we live in this, let's say, ocean, and if you throw a cold bottle in the ocean, pretty soon it's going to warm up to ocean temperature. Or if you throw a hot bottle in the ocean, it's going to cool down. And there's going to be a thermal reservoir. And so this system is not going to stay cold forever if there's thermal contact between the system and the surroundings. If the surroundings has plenty, it's a reservoir of energy, then what's going to happen is the system is going to warm back up. If the system warms back up here, so we'll take this system and warm it back up to here. I'm keeping the same volume. If we go back to the same temperature, then they're going to both have the same kinetic energy. And so this is what we call isothermal expansion of the gas. Isothermal expansion of the gas is the initial temperature and the final temperature are the same. There's no change in temperature. And that's because we live in a heat reservoir called the surroundings here. So a sample of an ideal gas is allowed to expand at a constant temperature. So this is isothermal, constant temperature. Does the gas do work? Did the gas do work when it expands? The system, which is the gas, blew up the balloon. In order to blow up a balloon, do you have to do work? And so, part A, does the gas do work? Yes. Part C, what happens to the temperature of the gas? Well, an ideal gas here, if it does work, it's going to lose energy. If it loses energy, it loses kinetic energy. If it loses kinetic energy, what happens to the temperature? The temperature decreases. However, it's short-lived because it's in a sea a thermal reservoir, which we call the surroundings. And so it can't stay cold because the surroundings is warm. And so if the surroundings is warm, then some of the heat from, or the energy from the surroundings is going to go into the system to warm it back up. And so what we can say is, what happens to the temperature of the gas? It initially gets cold, and then it'll warm back up as it absorbs energy from the surroundings. And so that's what we say for C. B, does the gas exchange heat with its surroundings? Yes. What is delta U for the gas? That's a D. Well, it depends here. If we look at the initial expansion, delta U is negative because we're losing energy. We had to do work. But if we look at the overall process, that is the expansion and then the warming back up of the gas, then delta U, well, they're at the same temperature. If they're at the same temperature, they're at the same kinetic energy. If they're at the same kinetic energy, then delta U is 0. And so delta U is 0. And so if we look at the overall process, does the gas do work? Yes. B, does the gas exchange heat with its surroundings? Yes. What happens to the temperature of the gas? Well, initially it cooled down, but it's going to warm back up the same temperature. What is delta U for the gas? Initially it was negative, and then it goes positive because it absorbs heat from the surroundings. And so delta U overall is 0. Okay, that's when it's inside this thermal reservoir of the surroundings. However, what if we isolate it from the surroundings? That is, we put an insulator barrier here so that the surroundings can not exchange heat. And so it doesn't matter if the system is cold and the surroundings hot, there's not going to be an exchange because it's thermally isolated. Okay, so that is what we call adiabatic process. Adiabatic means there's no heat exchange with the surroundings, or between the system and the surroundings. In an adiabatic process, the system is thermally insulated. There is no exchange of heat between system and surrounding. For the adiabatic expansion of an ideal gas, does the gas do work? So adiabatic means we ignore the surroundings now and just look at the system. So if the system expands, was work done by the system? Yes. And so does the gas do work? Yes, it expanded. B, does the internal energy of the gas increase, decrease, or remain constant? So if the gas expands, its internal energy is going to decrease because it's losing energy doing work. And so what we say is it decreases. If the internal energy decreases, the kinetic energy decreases. Kinetic energy decreases, the temperature decreases. C, what happens to the temperature of the gas? It decreases, it gets cold, but there's nothing to warm it back up. It's thermally insulated, so it gets cold and it's going to stay cold, okay, until something goes out there and warms it up.
Is that, remember that one, number 58, is that one true if it's not an ideal gas?
If it's a real gas, then there are other things that we have to worry about. If it's a real gas, then there's potential energy involved, but warming or cooling it down is not really going to impact it. The problem with the potential energy is, if the potential energy could be from the bonds aren't going to change here, but it also could be from the intermolecular forces. And so what we're going to do is, if the gas is more compressed, then the particles are closer to one another. If the particles are closer to one another, then they can potentially stick to one another. And so we have to worry about intermolecular forces, IMFs. And those intermolecular forces are going to change. So when we have a change here, it's not going to be solely in terms of temperature. It could also be in terms of potential energy as you break the molecules further apart from one another.
Is it wrong to say that that it's still gonna get colder?
No, it's still going to get colder.
You just don't know how much.
Yeah, it's not going to be the same. Well, it depends on, because real gases can behave ideally. And so it depends on your initial temperature and pressure. If you're at a pretty high temperature and a low pressure, then it's already pretty ideal, even if it's a real gas. And so real gases behave quite similarly. So. Well, let's take a look at 59. Do you think the following observation is in any way possible? Or going back to real gases are more alike than dissimilar. I mean, they're more similar than dissimilar. Do you think the following observation is in any way possible? An ideal gas is expanded isothermally and is observed to do twice as much work as the heat absorbed from its surroundings. So if it did twice as much work, this is isothermal, so it can absorb heat and warm back up. So this is our delta U here, which is going to equal Q plus W. And basically in this delta U, we're just doing work. Yeah. And when we do the work, it's going to cost us some amount of work to expand that. But it says we're going to do twice as much work as heat is absorbed from the surroundings. So let's say we did, we lost 100 joules in doing the work. But we're only going to absorb 50 joules from the surroundings, because we're going to do twice as much work as heat absorbed. Are we going to get back to the same temperature? No. You see, we're not going to make it back to the same temperature. We're going to be here. Isothermal means the temperature doesn't change. And so, is it possible to do this isothermally? No. It is possible to do this. Yeah, you could do twice as much work as heat is absorbed, but you aren't going to get to the same place. So if we do 100 joules of work here, we're going to lose 100 joules. But we need 100 joules of heat to bring us back to the same temperature. Does that make sense? And so this is impossible because we aren't going to get back to the same temperature. Do you think the following observation is in any way possible? A gas absorbs heat from its surroundings while being compressed. This one's a bit tricky to think about. So if we compress a gas, who does the work? The surroundings does the work. And so the system is going to benefit from gaining energy. In other words, the system is going to have work done on it, so it's going to gain energy here. It depends here. If this is our system, and this is our surroundings here, initially the system and surroundings are in thermal equilibrium. They're at the same temperature. But if you compress the system, well, it depends on how big the surroundings is. See, the surroundings is quite big. Then the system's going to get hot. If the system gets hot, will heat be exchanged from a cool surroundings into a hot system? Does heat move from cold to hot or from hot to cold? Hot to cold. And so this is wrong. This is the wrong direction. Heat is always exchanged from the hotter body to the colder body. In other words, the hot body is going to get colder and the cold body is going to get warmer. What they're saying here is that the hot body is going to get hotter and the cold body is going to get colder. Does that make sense? Well, it makes sense if you have an air conditioner or a heat pump or something like that, but it's not going to make sense spontaneously. Okay, so number 60 is a weird one, so don't worry about that one too much. Let's go to number 61. There are other forms of work besides PV work. Okay, I talked about electrical work and mechanical work, and so 61 is electrical work. For example, electrical work is defined as the potential, which is voltage, times the change in charge. Change in charge. This is not heat, delta Q. This is charge. Charge is measured in coulombs. So if a charge in a system is changed from 10 coulombs, this is on degree C, to 5 coulombs, in a potential of 100 volts, 45 joules of heat is liberated. What is the change in internal energy? So we can see here, or at least calculate it. So the calculation is kind of similar to what we did for P delta B. We aren't going to worry about the calculation so much. We aren't going to do these types of calculations. This is just showing you how it would be done if you were to do calculation for electrical work. Another type of work is mechanical work. And so this is a kind of an interesting example of mechanical work. Another form of work is extension, defined as tension times change in length. So work is a force, the change in the length. So you're pulling something apart or stretching it. A piece of DNA has an approximate tension as a force of 10 piconewtons. Newton is a unit of force. What is the change in the internal energy of adiabatic stretching of DNA by 10 picometers? And so we can calculate how much energy it takes to stretch the DNA by 10 picometers, if we wanted to. And so these types of equations you don't have to memorize. This is just so we can do the calculations if we need to. Then we finished these. Is that correct? 66, we finished that? And we were looking at problem 108, I think. Is that right? Let's finish problem 108. So this is metabolism of glucose. This is a solid. Did we already do this here? The relationship between delta U and delta H? So what are all the ways of getting delta H? Delta H is the same thing pretty much as QP or QV. QP. And so if we do constant pressure calorimetry, we can measure or the temperature change, and we can relate that to Q, the heat, either as a process or an object. And so what we want to do is we want to do constant pressure calorimetry to get delta H. But when we burn things, it's not so easy to burn at constant pressure. So we end up doing constant volume, or it's another name for constant volume calorimetry. Bomb calorimetry, or QP is what we're going to measure. And so what we'll do is we'll do delta U. If we do delta U in a bomb, can the volume change in a bomb? No. And so we do bomb calorimetry, then delta U is equal to QV, because in a bomb the volume can't change. And we're not doing electrical work, and we're not doing mechanical work, and so it's just QV. Once we get QV, then we can normalize it. That is, we just go QV divided by the amount. And so if we burn 1 gram of glucose, then this would be however many joules per gram or kilojoules per gram. But usually we don't write kilojoules per gram, we write kilojoules per mole. So we'll just convert it from kilojoules per gram to kilojoules per mole, and that gives us our delta U in our usual units of kilojoules per mole of glucose. 1 mole of glucose requires 6 moles of oxygen and produces CO2 and water, 6 moles each. But you know what? We don't want delta U. What we want is delta H. And we know that delta H is equal to delta U minus W. So delta U we can get from calorimetry, bomb calorimetry. How do we get W? Well, we're dealing with delta H, then delta H is the energy change under conditions of constant pressure and only what type of work? PV work. And so we can get W by calculating delta V, the change in volume. And so let's take a look at delta V. Gases are going to make the biggest change in volume. So we have 6 moles of gas here. And final, we have 6 moles of gas. And so delta V is essentially 0 or close to it. Because the solids and liquids, they aren't going to have much of a difference in volume. And so what we can say is that delta U and delta H are about the same thing, basically, for this particular problem. And so one way of getting delta H for glucose is by burning it in a bomb and then calculating delta U and then converting it to a delta H by determining how much work. In this case, the work is close to 0. The work is close to 0 because the volume doesn't change much. But it still requires doing bomb calorimetry. So maybe we can avoid it. They give us a delta H here. Is this delta H a combustion of glucose? No, this is delta H of formation. Delta H of formation, did I write the reaction down already? The equation for delta H of formation of glucose? Yeah, okay. It's a different reaction. We need the combustion. And so here, if they give us delta H of formation, then chances are we can do this using Hess's law version 2. If we use Hess's law version 2, then delta H for this reaction is equal to the delta H's of formation of the products minus the delta H's of formation of the reactants. Did I already write this on the board?
We didn't get that far.
Okay. So I'm going to use Hess's law version 2, because that way I don't have to do calorimetry. I don't have to do any of this stuff. I can just go ahead and calculate my delta H. And so it's going to be the products minus the reactant. So the products I have are 6 moles of CO2 times the delta H of formation of CO2. This is going to be under standard conditions because our data table has under standard conditions. So this is delta H naught of combustion here for 1 mole of glucose. All right, plus 6 moles of H2O, liquid, times delta H of formation of H2O liquid. Okay, that's my products minus the reactants. The reactants, I have 1 mole of glucose times delta H of formation for glucose. Plus 6 moles of oxygen times delta H of formation for oxygen. We already know one of the numbers, delta H of formation of oxygen. What is the delta H of formation of oxygen? 0. The formation of an element, so the formation reaction would be forming 1 mole of the element, whatever, no, excuse me, 1 mole of oxygen from the elements in the most stable state. The element in the most stable state would be oxygen. So this is going from oxygen gas to oxygen gas at 298 Kelvin. Is there any change in energy? No, I mean, it's the same thing. And so the change in energy here, delta H is equal to 0. And so that's why. The others we'll have to look up. The delta H of formation of glucose was given. And that's minus 1273.3 kilojoules per mole. So we need to look up the delta H of formation of CO2 gas and the delta H of formation of H2O liquid. And so here we have to go to appendix D. They don't give us the numbers in the problem. And so let's go to appendix D. So the delta H of formation of CO2 gas is minus 393.5 kilojoules. Minus 393.5 kilojoules per mole of CO2. And let's go to water. All right, we're going to H2O liquid, which is minus 285.8. H2O gas is a different delta H formation. H2O liquid, minus 285.8 kilojoules per mole. And H2O solid also has a different delta H formation. They don't show it here because the solid is not stable at 298. This data table is for 298 Kelvin. All right, so let's calculate it. Can somebody calculate this? Is that what you got? Okay. This is for the reaction as written. It's 2002.5 kilojoules. All the moles cancel. But when I look at the reaction as written, it's for 1 mole of glucose. And so what I could do here is I could just say 4 minus 2802.5 kilojoules per mole of glucose combusted. Our calculation was based on 1 mole of glucose combusted. And so I'm going to reinsert the mole, even though it's canceled out. Because energy is extensive, so we need to know, the amount of whatever is for that energy. Okay, so a mole of glucose weighs about 180 grams. So if I burn 180 grams, I'm going to get this much energy. But I can burn it in a fire, a flame, I'll get that much energy, or I can burn it in your body. And if you burn it in your body, you'll get the same amount of energy. That's because it's a state function. And the state function doesn't matter. It just depends on the initial and the final state. So you can eat some glucose, inhale some oxygen, exhale some CO2, produce some water and energy. Or you can throw the glucose in the fire. So it doesn't matter if you do this in 1 step or 100 steps, we'll get the same amount of energy. And so when we metabolize it in our body, we should get the same total energy. Well, however, how you use that energy, it's not all heat. And we'll do some work as well. And so let's see what they're asking here. Heat released in the process is converted to useful work with about 70% efficiency. It's not really heat that's released. So for example, it's not like you eat this stuff and all of a sudden you get super hot. And you get super hot and then you convert all that heat into mechanical work. No, it's not that way. What it is we're converting chemical potential energy into work. And so it doesn't go from chemical potential energy into heat then into work. If we went from chemical potential energy into heat and then work, we can't get this kind of efficiency. This is 70% efficiency. We typically get much lower efficiency. Those are called heat engines. And heat engines have notoriously bad efficiency. Instead, what we're going to do is we're just going to go directly from chemical potential energy and then try to convert this into work. And so there's some work that's unavoidable. And the work that's unavoidable is already incorporated in delta H. And that's the PV work. In this case, there wasn't much PV work. And then all the rest of the energy we can use. So we call this the net energy. Net energy is equal to gross energy minus the tax. In this case, there's no tax. Okay, what can we do with that energy? Well, it doesn't all have to be heat. I know this is called heat of reaction, but what we can do is we can just do more work. The more work we do, the less heat we're going to get. And it turns out, how much work can we do? Well, in the body, we can use about 70% of that energy as work. Okay. Calculate the mass of glucose metabolized by a 58.0 kilogram person in climbing a mountain with an elevation gain of 1,450 meters. Assume that the work performed in the climb is about 4 times that required to simply lift a 58 kilogram mass by 1,450 meters. And so there's some physics involved in this problem. The physics you don't have to know. We have chemical potential energy, like glucose and oxygen have a higher chemical potential energy than CO2 and water. But in physics, the potential energy that they focus on is gravitational potential energy. So let me talk about gravitational potential energy first. Let's say you have 2 diving boards. Let's say there's a diving board here and a diving board here. This diving board's higher than this diving board. Let's say they're at the same temperature and they're not moving. So the kinetic energy is the same. What's the difference? The difference is in potential energy. And the difference is in something called gravitational potential energy. The gravitational potential energy is given in physics by this equation, mgh, where m is the mass. So if we had a person here and a feather, a bird feather, and the bird feather flew down from here and hit you on the head, are you going to worry so much? No. But if the person fell down and hit you on the head, it would hurt. And that's because they have different gravitational potential energies, because gravitational potential energy depends on the mass. And a feather doesn't have much mass. A person has a lot more mass. It depends on G. So if they were on the moon, it would hurt a lot less because the force of gravity on the moon is 1/6 that of the Earth. So you're a lot heavier on Earth than you are on the moon. And so we have G. G is always trying to pull you to the center of the Earth. And then when we have the height, this person is going to be at a higher gravitational potential energy than this person because they're up higher. So we can calculate how much energy does it take to climb from this perch to this perch. It would be the difference in gravitational potential energy. Well, if this person doesn't lose any mass, then the mass is constant. The force of gravity will just say is constant over this range. And so the difference is the height, this height versus that height, or delta H. And so it's going to depend on how much they had to climb. How high did they have to climb? And that's going to be the energy. And the energy is going to be given in SI units. M is in kilograms, G is in meters per second squared, H is in meters. So the units for gravitational potential energy are kilograms, meters squared per second squared. Have you seen that before? What's that called? A kilogram, meter squared per second squared. That's called a joule. This is defined as the joule. 1 kilogram meter squared per second squared. So we have a 58.0 kilogram person. Climbing a 1,450 meter mountain. Here. The difference in energy here is going to be the difference in height, delta H. And so how much energy this is going to take is going to be the mass, 58.0 kilograms, times G. G is 9.81 meters per second squared. And the height, or how much they had to climb, 1,450 meters. So what does that come out to? So we're going to get 58 times 9.81 times 1,450. Kilograms. 824,180 joules, or 824.2 kilojoules. This is the delta E or the delta U. Delta U and delta E are often taken as the same thing. Change in energy, change in neutral energy. But this is like if this person rode a frictionless elevator. If the person rode a frictionless elevator, that's how much energy would be required to make that climb. But this person's climbing this, and they're probably climbing this by some kind of circuitous route. And so they're probably going to end up spending a lot more energy than you'd normally think, having to walk a longer distance. And so we're going to assume it's going to take 4 times the amount of energy. This would be the minimum energy, but we doubt you can get up there with a minimum energy. We're going to need extra energy. It could be wind and whatever. So we're going to do 4 times our delta U or delta E, which is going to be 4 times 824.2. kilojoules. So times 4 is 3,296 kilojoules. $3,296.7. So we're going to estimate about 3,300 kilojoules are required for the climb. That estimate's coming from what they tell us. Assume that the work performed in the climb is about 4 times that required to lift the 58 kilograms by 1,450 meters. Okay, so this is a standard. If we require this many kilojoules, how much glucose do we need to consume? And so 3,296.7 kilojoules required. That's how much energy is required for this climb. But when we metabolize glucose, it's not with 100% efficiency. When we metabolize glucose, can we use all that energy for work? No. How much can we use for work? Only 70%. So we're going to get 70% for work, 30% is going to be for heat. And so that means this. That means for every 100 kilojoules of delta H, only 70 kilojoules can be used for work. So for every 100 kilojoules of delta H, 70 kilojoules can go to work, 30 kilojoules for heat. And so that means we actually need a lot more kilojoules because, so this is going to be times 100 divided by 70. We're going to need 4,700 kilojoules. We're going to need 4,700 kilojoules because 30% of those kilojoules will be wasted. Not really wasted, but will be converted into heat. And I think you need heat to maintain body temperature in this climate. It's not totally wasted. Then what was delta H? So for every 1 mole of glucose, how many kilojoules do I get?
2,000.
2,008.
2,802. 2,802.
Oh, so 2 kilojoules. Okay.
2,800 to 2,802.
2,802. 2,802. Okay. Is that right? Okay. Per mole of glucose. Now, what do we do with the sign? Can we have negative grams? No. So we could do different things with the sign. One thing we could do with the sign is say, okay, this has got to be negative because this is the amount of heat that has to be released from the glucose. And so it'd be a negative and a negative here, which would make it positive. The other thing we could do is we could do this verbally. That is, this is the amount required, and this is the amount that gets released when we consume it. So we make it positive, positive. We change the sign that way. And so this is often done. what we do is rather than put the negative there, we say it's evolved or released. That was like in the first law problems that we did earlier. You know, they said 58 kilojoules were absorbed, or 58 kilojoules were evolved. You know, and then we do the sign. And so here we're putting in the words and getting rid of the sign. But you have to be very careful, you know, because for a lot of math, we need the negative sign in there. And so if we're to keep or retain the negative sign, then the minus, this has to be minus because we're looking at it from the standpoint of the system. You know, the system's got to lose this much net. In order to lose this much net, it has to lose 4,600 gross. And that's going to come from this. So we can put negative and negative, or we can put positive and positive. All right, and then I need the molar mass of glucose. So I don't know how to calculate it. I'm just going to look it up. The molar mass of glucose is here. $180.2. So 180.2 grams per mole of glucose. So how many grams do I need? Here. So it's going to be 3,296.7 times 100 divided by 70 divided by 2802 times 180.2. $302.8 grams. Looks like we're allowed about 2 sig figs. So about 300 grams, 3.0 times 10 squared grams of glucose. 300 grams of glucose. All right. Okay, any questions on this?
In the second or the first conversion factor, the delta H and the work, do we have like factor those into the units?
What do you mean by factor?
Because we want to cancel the units.
Oh, I see what you're saying. Yeah. This is the kilojoules for work, actually. All these kilojoules are being used for work and climbing the mountain. None of it's being used for heat. So this is work. And then the delta H is going to equal our delta U minus W. This W is already used up because this W is the mandatory work to maintain constant pressure. And so really this delta U is Q plus W minus this W. And so this W is already taken care of in the delta H. And so what we're looking at here is this. And so in this case, it's going to be 70% work here, 30% heat here. So we're converting all our delta H, because this is gone now, into heat and work. Originally, this is just heat, QP. Does that make sense? And so this conversion factor here, it works out because this is the available energy. Delta H I call the available energy. The available energy is going to be the total gross energy minus whatever tax we have to pay. The tax has already been paid, and so we're looking at the available energy, delta H. That delta H, which we often call QP, doesn't have to be all heat. This is 100% heat. Instead, what we could do is we could take that QP and use some of that for work. And so if we take that energy, which would have went to heat, and say, okay, I don't want it all to go to heat. We're going to keep it at 30% heat and 70% work. And so I took my available energy and divided it into the 70% for work. I'm only going to get 70% for work. The other conversion factor is for every 100 kilojoules of available energy, I'm going to get 30 kilojoules of heat. And so the units work out. This is the amount of work I need to do. This is kilojoules of work. And the delta H is the total available energy. Well, that's what we get from calculating delta H using Hess's law version 2. And so the units do work out, actually. Might not look like it.
So we're going to say that 2002 kilojoules released is 2002 kilojoules of available energy.
Of available energy. The tricky thing here is this available energy, which is QP, it doesn't have to be left as heat. You know, what we're going to do is we could just burn the glucose and convert it 100% to heat. That's what we get there. But what instead we could do is convert that chemical energy change into work. You know? When we do delta H, we only factor in one type of work. The work that we do here is P delta B work, so it's minus and minus P delta B. That's this term here. But we can do other types of work in addition to P delta B work. And if we have other types of work in addition to P delta B work, well, we can't avoid this. So this is what we call the mandatory work. Okay, we can do other types of work, and this would be the work of climbing, which would be mechanical work. Let's see, for mechanical plus gravitational potential work. And so that means we're going to get less and less heat as we do more and more work. And delta H is often called the heat of reaction, but it doesn't have to be 100% heat. All right, we're going to look at, or start at chapter 8 here. The weird thing is light comes in little packets, and these packets are called photons. Photons is quantization. Quantization, or quantum, means that it's discontinuous, not continuous. That is like this. In Chem 4, they show quantized gravitational potential energy. Here, we can't have any gravitational potential energy you want. It depends on what step you're on. So we could have this gravitational potential energy, but the next allowed gravitational potential energy will be here, right? And so this is quantization of energy versus this. Here we can have any gravitational potential energy we want. Depends on how high up the ramp we want to go. So all gravitational potential energies are allowed from here to here. And so this is what we call a continuous spectrum or continuous range or continuum of energies. Here we have quantized range. Now, does that mean there are gaps in the electromagnetic spectrum? What I mean by gaps are there any forbidden energies of light here. Do we see any quantization? That is, okay, we can have infrared, but then it's going to have to jump up to ultraviolet and sit visible. Or is it a continuum of energies? In other words, are we allowed a continuum of energies of light all the way from radio to gamma? And the answer is it quantized or a continuum? It's quantized, but what's forbidden? Do you see something that's forbidden or quantized? I don't. And so it's weird. Light is a bit weird. And so what we say is this. I'm going to call this a radio photon. A radio photon is low energy. And the size of the circle is going to represent the amount of energy. And then this is a gamma ray photon, which is going to have a lot more energy. And so when I go from radio to gamma, there are no forbidden energies. In other words, we have a continuous spectrum of energies, or continuum. In fact, when we look at the rainbow, all colors of light are allowed in the rainbow. And so how's it quantized? How it's quantized is this. When I have a gamma photon like this, I can't have any energy of gamma photon I want. If I have one of these, what's the next gamma energy allowed? The next gamma energy allowed will be 2 of these. I can't have 1.5 of these. But that energy is allowed because 1.5 would be the equivalent to 1 of these. Something like that, or 1/2 of it, or whatever. In other words, actually 1.5 would be over here. And so I have a continuous light spectrum. That is, I can have any size photon I want. But once I pick one size photon, then I can't. These are going to come in integer multiples. So it would be 1, 2, 3, 4, but nothing in between. And so in this sense, light is quantized. And so let's say I'm looking at a red photon here. And that red photon is going to have some energy here. Well, the next allowed energy for this red photon's wavelength will be 2 of these, 3 of these, 4 of these, 5 of these. And so this is the way energy is quantized. I have a continuum of energies allowed for light, but once I pick a certain size photon, then it's going to be quantized. Does that make sense? So anyway, we're out of time, so I'll talk about this next time.